Okay, hello everyone and welcome back to your YouTube channel and welcome to this amazing video today. As you must be aware, I am recording this lovely series of videos related with electromechanical conversion systems. And one very important aspect when you are working with electromechanical conversion system is related to the efficiency and the power losses. So today I have this fantastic video for you that is basically a practical example, numerical example connected with the concept of iron losses in magnetic material. And without further delay, let's start reading this very specific statement. A typical 1 MVA transformer has a weight between 6,000 and 7,000 pounds. In kilograms is 2,800 to 3,500. This weight from the transformer is, I will say, probably in large proportion related to the magnetic core of the transformer. So we know that the iron loss generated by 2,800 kilogram samples of material used on the magnetic core of a transformer is 2,250 watts when subject to a 60 Hz magnetic field. So the relative permeability of the magnetic material is 7,950, and the statement equation describing the power losses is presented here. As you can see, this is basically the equation coming from statements. We have a coefficient over here. B represents the magnetic flux density. We have one exponent here, and then the frequency in hertz, and then another exponent. Something that you need to note is that this equation is the active power density losses, because in this case, the equation is describing watts per kilograms. So below, there is a very interesting question. Calculate the magnetizing field H in amps per meter. So it's a very simple but very interesting problem, because to calculate H, the magnetic field strength in amps per meter, we need to know B, that is the magnetic flux density in Tesla. And the connection between B and H is the absolute permeability of the material. So what I'm trying to tell you is that we need to use this statement equation to obtain B, and then with B and using the absolute permeability, we can obtain the magnetic field strength. Okay, as you can see over here, I am using this very useful and powerful tool from MATLAB. This is a MATLAB Live script. A MATLAB Live script is one of my favorite tools when I am teaching practical example to my students. And basically, a MATLAB Live script allows me to include tests in order that I can explain my ideas to the students. At the same time, I can insert equations with the very proper format for those equations, but also it allows you to include some figures, some photos, or audio in order to enhance the learning experience of my students. So today we will start the solution of this very interesting problem related to iron losses and magnetic field strength. And we will start here by defining the input data or the known data, okay? As you can see, I am defining here W like the weight of the magnetic material sample in kilograms. And as you can see, this is 2,800. Then we are defining the total iron losses. For this case is 2,250 watts. We are defining also the relative permeability. For this example is 7,950, and this is just a number without any units. And finally, we are defining the signal of this magnetic field, the frequency, and in this case, the frequency is defined in hertz, 60 hertz. So the starting point for the solution is, I would like to remind you the whole equation of the statement equation for active power losses, iron losses. So we have here a coefficient Ki that is 0.06. We have a magnetic flux density that is the value that we are interested in calculating. But we have the exponent A that is 1.67, and also we have here the frequency 60 Hz and the exponent that is 1.22, and we are using the letter X. So again, the situation here to obtain the magnetic field strength, well, we need the permeability of the material, but also more important, we need the magnetic flux density. So the first step here is we want to define the permeability of the vacuum. And all my students, they must remember from the classes, the permeability of the vacuum is a constant and the numerical value is 4 pi exponent minus 7. So as you can see over here, I already defined inside the MATLAB live script the value of this very important constant, and that is the permeability of the vacuum. Now, what I will do is I will calculate the absolute permeability of the material. And in this case, to calculate the permeability, the absolute permeability, what I need to remember is multiply the relative permeability by the permeability of the vacuum. And in this case, the relative permeability, we already know that from the statement, is 7,950. And we know because we already defined the permeability of the vacuum for pi exponent minus 7. So as you can see, the absolute permeability over here is 0.01. The next step is probably the most lovely step here in the solution. Because right now you need to apply the basic mathematics. And I am sure that all my students, they have so high level skill for working with maths. So what we need to do is, starting from here, from the statement equation, we want to extract the value of the magnetic flux density in Tesla. So to do that, what we need to do is basically extract this term over here. In other words, we divide in both sides by Ki and F exponent X. So here we have the extraction of this very interesting term, B exponent A. And I will call M for the whole number B exponent A, but after applying logarithm to both sides of the equation. In other words, M is basically what we know as the logarithm of this quantity B exponent A. Because when we know M, we will be able to calculate B. So here I put the final value for M as the logarithm of this coefficient or quotient here. So when you put the number together, you can do that at home. 2,250, the weight 2,800. You can see over here the coefficient Ka Ki, sorry, the frequency 60 Hz and the exponent 1.22. So by calculating this number, we obtain that the value of m is minus 0.04. So the final step here is to obtain the final magnetic flux density, and in this case is letter B in Teslas, of course, in Tesla. So what we need to do is use this expression over here, 10 exponent m divided by a, where m is this value that we already know, and a is the exponent that we already defined before, 1.67. So doing so, we obtain the amazing magnetic flux density, 0.9431 Teslas. So now we are almost finishing this problem, because finally the relationship between magnetic flux density and magnetic field strength is basically the permeability, the absolute permeability of the material. In other words, we divide 0.9431 Teslas by the absolute permeability that we already calculated before, 0.01. So we obtain here our result or answer, H equal 94.4042 amps per meter. I highly suggest to my students that in the exam paper, write near to the answer A, in order that I will be able to identify the solution. But coming back to this problem, I believe you can see that we develop equations in order to obtain B, and from B we obtain the magnetic field strength. To be honest, what I need is that all my students look at these equations and use paper and pen at home, and they must understand those equations, because this is basically pure basic mathematics in order to obtain the magnetic field strength. So sadly, we are reaching the end of this video. In this video, you learn how to use the statement equation for the iron losses in magnetic material in order to obtain the magnetic field strength. Well, I hope that the explanation is good enough that you understand all the concepts and you learn something from this video. And also, if you have any question or comment, please leave the comment up here at the video, or basically drop me an email. If you want to be more informed about activities related to research development and also teaching, please subscribe to the YouTube channel and also the LinkedIn community. But if you want to know in more active way what we are doing day by day in research, please subscribe to the social media, in particular Twitter and Instagram. Well, this is the end of this video. Thank you very much for watching, and I must say bye now.